40 past 2, 20 to 3. So we should finish at 4:10. At 4:10, 10 past 4. I remind you that the previous lectures were dedicated to the introductory notes, the general concept of nucleation, and to historic notes. So some short history of nucleation studies in Cherkasy and in the vicinity of Cherkasy. So that was it. I finished with this shortly. I will come back to these stories in much more details later, I hope. But today I want to start the regular course of nucleation in solid-state reactions. So, chapter 1. Chapter 1. Homogeneous and heterogeneous nucleation. Homogeneous and heterogeneous nucleation. In single component systems. Іноді замість single component, щоб коротше, я буду казати pure, да? Чистих. Хоч ви знаєте, you know that pure is some idealization, yes? Because in nature we cannot find any truly pure element, pure material. In any material contains a little bit dirt, some impurities. Why I am starting from single component materials? Because in this case, to nucleate the new phase, we don't need any diffusion. We don't need any redistribution of atoms. I mean long-range redistribution. Я буду іноді повторювати українською мовою. В чистих речовинах для утворення зародку нам природі не треба перерозподіляти атоми на довгій відстані. Тобто нам не потрібна макроскопічна дифузія. We don't need macroscopic diffusion for nucleation in single component systems. At first, today, we will consider mainly the thermodynamics of such kind of nucleation in single component system. And the next lecture, at least part of it, will be dedicated to the kinetics of nucleation in single component systems. So this was chapter, now section. Section це типу параграфу. Да? Section 1.1. Thermodynamics of homogeneous nucleation. Thermodynamics of homogeneous nucleation. In single component system. Поки що буду іноді повторювати. Отже, таким чином, термодинаміка гомогенного зародкоутворення у однокомпонентній системі. Actually, it's something like reminding you the standard material of standard course of thermodynamics in the fourth undergraduate year. Yeah. All of you were the students, undergraduates, and during the fourth year you studied statistical physics and thermodynamics. And one of the chapters of this course was nucleation. I'm talking about any case of homogeneous nucleation in single component system, but to be concrete, to be more straightforward, I will call this nucleation crystallization. So I will consider as an example of such transformation, the transformation of liquid into solid, pure liquid into pure solid. freezing. Yeah? Nucleation of freezing. If we treat thermodynamics, we should, of course, start from thermodynamic functions. So I just remind you the dependence of Gibbs free energy per atom as a function of temperature at fixed pressure. Since crystallization is a first order transformation, it means that two phases, crystalline and liquid, can coexist within some finite temperature interval or temperature range. Я повторю українською мовою. Оскільки кристалізація – це процес фазове перетворення першого роду, то це значить, що дві фази – кристалічна і рідка – можуть співіснувати в певному скінченному finite інтервалі температур. And I draw this. Just to be sure that you understand me, I tell you that one of this curve corresponds to liquid, another to solid. Please, Yura, tell me, this curve, to what phase does it correspond? To liquid or to solid? This liquid. Correct, you're right. This is liquid, this is solid. I remind you that minus dg dt, the first derivative of Gibbs free energy per atom over temperature, is just entropy per atom, which we denote as S small. And of course, we know that entropy of liquid is larger than entropy of solid at the same temperature, if you take the same temperature and pressure. So, therefore, this curve should be more steep, більш крута. Да? Рідині завжди відповідає більш крута залежність. And so, there is, of course, some intersection at some temperature, and this temperature is an equilibrium temperature of crystallization. And, of course, if you go from low temperature to high temperature, it's Tm, melting point, equilibrium melting point. Of course, if you want to consider the crystallization, we need to go left. You know that water never freezes equally at 0 degrees centigrade. To obtain the ice from water, we need some temperature below 0. Yeah? So, and this we call delta T. So let it be this temperature Tm minus delta T. Переохолодження, yes? Overcooling or supercooling. This interval we call delta G, driving force, bulk driving force. So delta G, as a function of temperature, of course, is GL as a function of temperature minus GS as a function of temperature. So, as you can see, I define this as positive value. In many books, in many textbooks also, you can see delta G as GS minus GL, and it's less than 0. But I don't like to operate with negative values, so I denote delta G as positive. Yeah? So liquid. So forget about this for a while. You can think about this when you see some textbook in which this delta G is defined in this manner. So, in this course, we will neglect the faceted shape of the nucleus. Ми будемо нехтувати фасетованою формою зародка. So, strictly speaking, the nucleus should be some faceted figure, yeah? Багатогранний такий. But this faceted figure is not far from sphere, and in most textbooks we treat this faceted nucleus as approximately spherical nucleus. In this case, we consider the change delta G. We consider the change of total Gibbs free energy when we have the nucleation of one nucleus. So this is G after nucleation minus G old. G old is equal to N multiplied by GL, because old state was pure liquid. Before nucleation we had only liquid, so GL as a function of T. N is the total number of atoms in the system. So we take big system, so we can neglect the surface input. Тобто ми беремо настільки велику систему, що краєвими умовами можна знехтувати. Тобто атомів на границі великої системи набагато менше, ніж в об'ємі, і ми ними нехтуємо. So what is G new? G after nucleation. G after nucleation is N capital minus N small multiplied by GL. N small is a number of atoms which were organized in the new structure in crystal. So N capital minus N small is a number of atoms in the old phase which still coexists with new phase, plus N small multiplied by GS. N is a number of atoms belonging to the new phase, to the nucleus of new phase. GS is a bulk Gibbs free energy per atom in this new crystalline phase. But I remind you that this is, of course, a favorable event, but for any favor we used to pay. Here we pay for this favor by surface term. So, because due to this term, the Gibbs free energy of the system goes down. But of course, if we have now some nucleus, some region of the new phase, which is crystal, and around we have liquid, it means that we formed the interface. And interface is a defect, and defect usually has additional energy, internal energy and Gibbs free energy. So we add the third term, which is gamma SL, multiplied, if we take spherical form, 4πr squared. And if we take, as I mentioned already, the spherical form, then N is 1 divided by omega multiplied by 4 to 3 πr cube. So number of atoms is just volume of nucleus divided by atomic volume. It's a volume per one atom. In this simple model, presented by Gibbs more than 100 years ago, actually about 140 years ago, we just approximately treat atomic volume as the same for crystal and liquid. Usually, of course, there is some difference within 10%, very frequently within 5%, but it's not that important if you don't have the stress. But stress is a story for future, not now. So if you combine this, and this, we come to the well-known equation. Delta G is equal to, since I already made this, I wrote this few lectures ago, so I am not writing the details, yes? It's okay? It doesn't mean легко видеть. So I already demonstrated this at the first lecture. Я це показував. So, but I promise you, starting from this lecture, to be honest and to try to derive everything. Sometimes I will ask you to derive at home and to prepare presentation, short presentation about derivation. The first experiment will be today. We will come to this. So if you combine this, and this, we come to the equation very famous for more than 100 years, is minus delta G divided by omega multiplied by 4 to 3 PR cube plus gamma SL, solid liquid, multiplied by 4 PR squared. All the rest of terms are cancelled. Yeah? Cancelled. And this is famous equation and famous plot, which I also I told you at the first lecture, that this plot is of course a combination of quadratic and cubic parabolas, and so we have something like this. And this dependence is characteristic for nucleation. We have barrier. So for small sizes, this curve increases, and then after reaching some critical size, are critical at some height, which is called delta G star nucleation barrier, it goes down. Since you remember, I called nucleation a miracle. It's some miraculous event, чудо, diva. And I remind you this phrase, which I like to repeat many times, that nucleation is an example how the nature can violate how the violation of some law provides the validity of this law. Як порушення закону дають можливість цей закон виконати. Because any nucleation means going against the second law of thermodynamics. So if by some miracle, which is called heterophase nucleation, the nature forms some undercritical nucleus, it's favorable for nature to dissolve this, to go down. If by some another heterophase fluctuation the size of the nucleus is overcritical, then it's favorable for the nature to go down, but now it means grows. So overcritical nuclei tend to grow, undercritical nuclei tend to dissolve. to shrink zjužovac, zmenšovac. And you know this very well from the 4th year of undergraduate studies. Now, I'm not talking today about kinetics. I promised you to talk about kinetics in the next lecture. But I will say you something kinetical. There is a well-known semi-empirical rule which is formulated in the following way. If it's not proved rigorously even now, but it works. If the nucleation barrier is higher than 60 kT, this is the Boltzmann constant, and this is the temperature of nucleation. If the height of nucleation barrier is larger than 60 kT, then the nucleation is practically impossible within reasonable time. Так трошки неконкретно говориться, але повторюю, це реально працює. Це реально працює за того, що тут всі залежності експоненційні, дуже швидко все змінюється. Why it is so? And we will use this criterion today. So then, nucleation is practically suppressed. How can we find the height of nucleation barrier? I remind you that the critical size is determined from the condition of the zero first derivative, d delta g over dr over r at some critical size should be equal to 0, and since this maximum from the high mathematics of the first year of undergraduate studies, the second derivative, the maximum for maximum, should be negative. This is a condition for maximum. So if you take the first derivative of this function over r, of course we obtain minus delta g divided by omega 4 to 3p multiplied by 3r squared. Of course 3 and 3 are constant. Plus gamma SL multiplied by 4p multiplied by 2r, and this is equal to 0 if we look for zero first derivative. Of course, since the right hand side we have 0, we can cancel 4p. We can cancel. It's okay. We'll not cancel so far. We'll write it in the following way. So r here 2 gamma SL minus delta G divided by omega multiplied by r is equal to 0. So we have this equation for r. So the solution of this algebraic equation is critical size. We have formally two solutions. First is 0. Anybody of you can take the second derivative, and you will see that here the second derivative will be positive, not negative. So it's not maximum, it's minimum. So we are not interested in minimum. So this is not physically interesting for us. And the second root of this algebraic equation is, of course, well known, R critical equal to 2 gamma SL omega divided by delta G. Actually, I have already reminded you of this simple Gibbs equation few lectures ago, but today I want to go further. So where it is possible, I will try to make some numeric estimations. It's very important for physicists to feel the numbers, the orders of magnitude. So I need this equation. Of course, we can substitute this R critical here and here, and then we obtain delta G, not just delta G, but delta G star, so the nucleation barrier. Indeed, if you do this, we obtain delta G star is equal to, I am afraid that I should ask somebody to buy a couple of more markers. Кого я можу послати? Так, тільки не забудьте, бо я його розумієте, що я його зразу ж прикладу. Дякую. Thank you so much. So delta G star, is equal to, let me do this in the following way. 4p R critical squared, we have 4, we have p here and here, we have R squared, and here 3 is 2 plus 1. And so we took it outside the parentheses. Parentheses, я нагадую, це круглі дужки. Brackets це квадратні дужки. So under the brackets, under the parentheses, we have minus delta G divided by omega, multiplied by 1 to 3, multiplied by R critical, the rest is here, plus gamma SL. And it's equal to 4p R critical squared multiplied by minus delta G 3 omega multiplied by R critical, which is here, 2 gamma SL omega divided by delta G plus gamma SL. Of course, we have omega cancelled, we have delta G cancelled, and minus 2 by 3 plus 1 is just 1 to 3. And so we have the famous equation, which doesn't depend on the shape. It can be proved, but I never proved it in general case, but I proved it many times for some special shapes. So it's 1 to 3 gamma SL 4p R critical. So which means 1 to 3 surface energy of the critical nucleus. It's a rather general statement. So for homogeneous nucleation, the nucleation barrier is equal to 1/3, одна третя, 1/3 of the surface energy of the critical nucleus. It's valid for spheres, it's valid for cylinders, it's valid for faceted nucleus. Okay. Now, so if we substitute this, we obtain gamma SL divided by 3, 4p, this 4 gamma SL squared omega squared divided by delta G squared. So it means 16 pi, sorry, not p by pi, divided by 3 omega squared multiplied by gamma SL cube divided by delta G squared. This is the result, I remind you, for homogeneous nucleation, which actually never happens, almost never happens. Only in very pure and very small droplets of liquid in the special experiments, which is not so easy to realize. But nevertheless, theoretically, we should start from this simplest, theoretically simplest, but experimentally very difficult situation, because it's very difficult very difficult problem to escape, to avoid heterogeneous nucleation. We'll talk about this in a few minutes. Now, but it's not the end of the story, because I say that we should make some estimations, and we'll make them. We can estimate some gamma. Since my work is related somehow, and your work, by the way, also is related somehow to tin, solders to tin, I can say that gamma SL for tin is about 0.45 joules per meter squared. So this is gamma. Just write it down. It's estimation. I will check. I wrote somewhere, but I forget where I wrote this number, but I remember it. Okay. But what is delta G? Delta G depends on temperature. So it depends on overcooling. Now, what is delta G? Now I remind you shortly how to estimate delta G. Now let us come back to the definition of delta G. Delta G is G liquid at some temperature T melting minus delta T. Overcooling or supercooling. I don't know exactly, I don't remember exactly